Hello, this is Mark Summers. I'm presenting on Solidworks Flow Simulation today. I'm going to go through a couple dozen slides and hopefully get you some information that you didn't have in the past in using Solidworks Simulation, Flow Simulation. So let's go through the slides here. So we're going to be talking about in particular using Peltier devices, thermoelectric coolers, same thing, and heat pipes, and internal tube axial fans. And so let's move on here. Here's a little list of our topics. I'm going to do a quick introduction, talk about atmospheric water generation. That was what my thesis was on, and used Solidworks Flow Simulation to do some optimization doing that project. Talk about my actual test platform that I designed and built. I call it the digital twin. It's got the real hardware and we got the computer model, and the idea is that we're going to try to do optimization on the computer model before we build a bunch of different configurations, and then talk about in particular what I did in SolidWorks Flow Simulation, and then some closing thoughts. So introduction, this is some information on myself, my educational background. Work experience, I've worked in several different industries, including aerospace industry, semiconductor equipment industry, designing and building ion implanters for that industry. And last job I had before I got into teaching was automated test equipment. And there's a time frame spent at those places, and I've been teaching for the last 15 years or so at the community college and a 4-year university level here at Texas State University. All right, so let's talk about atmospheric water generation, kind of give you an overview if you don't know how that works. The idea is that we want to extract water, liquid water, from the air vapor, air vapor that's around us all the time. We've got a high humidity, we've got a high percentage of water in the atmosphere, in the air locally, and the way we get that water out, turn it from water vapor into liquid water, is to create condensation plates and extract the water that way. The motivation of the research was to use more environmentally friendly methods to get the water that's needed. And they have vapor compression refrigeration cycle units that are available, but the idea was to switch to a DC devices using Peltier effects that will let us do the same thing without having to generate a bunch of exhaust fumes and such. These TECs are very highly reliable, low maintenance, and so we'll be able to get away from using diesel generators to generate power, and instead use solar power to power these DC devices to get the condensation plate cooled down. So the optimization portion of the project, basically it boils down to one thing. You want to get the maximum, you want to minimize the power required to get 1 liter of water out of the air. So every time whether it's power for running the cooling fans or powering these Peltier devices, you want to use as little power as possible and get the most water that we can converted from water in the air into liquid water. We're going to evaluate various psychometric conditions. So different places in the world have different climate and weather location, depending on what location you're at. So we're going to look at psychometric charts and how we determine what's the best time to use one of these systems. And also optimize the number of Peltier devices we need on our condensation plate, so we can have more Peltier devices. We can cool the plate more, but it's going to potentially take more power. So trying to balance that as part of our optimization project. So a quick summary of the Peltier effect using these thermoelectric coolers. They have these couples, these P and N semiconductor couples, and you supply a DC voltage across the device, and it pumps heat from one side to the other. And these things, like I said, there's no moving parts. They're not as efficient as something like a VCR system, but they do have the added effect where they don't create any pollution, and they don't they're highly reliable and require low maintenance. And these devices operate at various voltages and current levels. And the way I measure the performance of these thermoelectric coolers is by coefficient of performance. And so Q sub C is the heat that's pumped between the hot side and the cold side, and you divide that by the input power that you're putting into the device, and that gives you this coefficient of performance that we want to get as high as possible. So continuing on, these are some data sheets from the manufacturer on these Peltier devices. There you can see the coefficient of performance on the vertical axis, and across the bottom is voltage. And you've got to have different families of curves depending on two things. Number one, the curves on the left, those two on the left, those performance curves when the hot side of the device is at 27 degrees C. And if the hot side of the device gets hotter, gets up to 50 degrees C, then you use the two curves on the right-hand side. And then looking up and down, the difference between the two curves on the left, on the top curve, those have certain delta T values. So the delta T across the from the hot side to the cold side, where that delta T is, you pick your family of curves to get your at a certain operating voltage, you get the coefficient of performance. So it boils down to you want to keep the hot side as cool as possible. So you keep that delta T low, and that will raise your coefficient of performance. So you've got to extract the heat from the hot side to get the cold side even colder. So that's the operating parameters of those devices. Now let's talk about psychrometrics. This is a psychrometric chart. These things are supplied. You get different charts depending on what the local atmospheric pressure is. This assumes we're at 1 atmosphere of pressure, and its value has several variables on these charts. So look at the bottom. Dry bulb temperature is the x-axis. Vertical axis is the humidity. You can see on the right the moisture ratio, and there's lots of other curves in there. You've got enthalpy, and here's a relative humidity curve, so you can see 10%, 20%, 30%. So it goes all the way over. When you get to this red line here, this is when you get to the dew point, when you start actually getting water coming out of the air. And so nothing really happens until you can get your condensation plate on this curve here. And we'll see in a minute how we go from one point to the other. But anywhere on this chart would be your local condition. So if you're at 40 degrees Celsius and you're at 20% humidity, then you would be right here on the curve, and you could read off your enthalpy, you can read off the dew point, you can read off all these other parameters. So once you have two parameters at a certain atmospheric pressure, you can gather all the other data from the psychrometric chart. So what I've done is created these charts here. This is superimposed on a psychrometric chart. I came up with an index to try to quantify how good the conditions are to try to extract liquid water from the air. And so these are three. There's a blue, green, orange, and red curves here. And the green curve I'll start off with. So we start off at 80 degrees Fahrenheit, and I think that's 50% humidity, if I can read this thing here. The green one's right here. So 80% dry bulb temperature, 45% relative humidity. That's considered the world conditions for these atmospheric water generation devices. So if you buy one of these things from a company, you want to get it rated at this world condition, which they consider it being 80 degrees Fahrenheit, 45 degrees relative humidity, and then they'll give you performance data on how much water it will generate with a given amount of power. So as you're starting from the conditions, say we're starting with this green star here, you start cooling down your condensation plates to try to get water to condense out of the air. You're having to put in energy, and you're having to extract heat from those condensation plates. And so when you're doing that, you're moving horizontally here. This is We're just changing the temperature, and we're getting closer and closer to 100% humidity. So you go straight across here as you're cooling your condensation plates. And as you go across there, you're spending energy, but you're getting no water. Once you get to this curve here, you continue to input energy, and your temperature can actually start going down, because the energy going in here is going into reducing the temperature, but you're not creating any water. Once you get to the 100% curve, you go down this curve here, and then you're generating water all the way down this curve. And my target temperature was 40 degrees Fahrenheit. You don't want to get it down to freezing, otherwise you'll freeze up your condensation plates, and that's no good. So the idea is that if you start like in this blue up here, the percentage of the energy you're putting in to get to the dew point, 100% relative humidity, is much less than the total amount of energy you're spending to get actual water. And so this point here at the top would be great if you had high temperature, high humidity. You wouldn't have to put in much energy at all to start getting water. However, on this red curve down here, you are starting at a pretty low temperature, and you're putting in all this energy all the way over to here to get to 40, almost 40, and you drop it down. You're only getting water for a small period of time that you're pushing energy in there. So the one at the bottom would be a low advantageous time to turn on your system. If you're in the middle or near the top, you're going to be able to get a lot more water out of the air with using less energy. And so I call it the Ronin index, ratio of needed enthalpy and net enthalpy. And I arbitrarily set this world condition. Turns out the Ronin value is 0.8. And by themselves, those numbers don't really mean anything until you compare them with one another. And so it's just the ratio of the energy going in to change the enthalpy on this part all the way down here divided by the amount that you're using to when you're not getting energy. So let's go to the next slide. Maybe that'll make this more clear. This is the spreadsheet that calculates these things, and I can type in numbers for the temperature, dry bulb temperature, relative humidity. This is one standard atmosphere, and it gives me this Ronin value here. And it's just the ratio of the change in this enthalpy divided by the overall change in enthalpy. And these curves up here, or these cells up here, give you the values. And so these numbers that are green here, these are what I call, good to better. This is around that 0.8 range. If you get really high temperatures and or mostly importantly high humidity, so over here on the right side is relative humidity, and on this axis down here is dry bulb temperature. And so if you got a condition, you can look up on the psychrometric chart, you can find this Ronin value that gives you one number to quantify how good one is to another. So if you've got 0.43 at one location and 0.88 in another, then it would be much more advantageous to turn it on in the green condition than the red condition. All right, so that's maybe enough about psychrometrics. Let's talk about this test platform that I built. Here's a CAD model of it, and it only shows there was 4 separate condensation plates. You can see this one has one Peltier device. This has 2, 3, and 4. There's 4 common fans. Each one of these condensation plates cooled with one fan, and of course you've got to have ducting that's different depending on how many of these Peltier devices you're cooling, and it shows a couple of them down here. And so we'll see some more pictures later about what those look like in detail. And it's got heat sinks in here to cool the backside of this thing. So let's go to the next slide and see some more details on this. This is an exploded view, and so here's my heat sinks and my heat pipes. Here's these fan assemblies and just one of the ducts. So this is just one of the 4 systems shown on here. And so if I click this, hopefully this thing will play, and we can see it go together. There we go. So the heat sinks bolt to the back side of the hot plate. The Peltier device is on the other side of the hot plate, and there's foam around to isolate the thermoelectric cooler so the heat doesn't get into the other part of the system. And so on the near side, There's a cold side of the Peltier device. On the far side is the hot side, and those condensation plates, those quarter-size condensation plates, are going to be on the cold side, and that's what gets cold. And then we're extracting the heat by blowing air across these heat sinks and these heat pipes, that we'll see here in a minute, to try to cool the hot side. So here's a picture looking from the front of this, what I call the hot plate. And so this is where the grids of these Peltier devices. So I have one of these, and these are 4 separate condensation plates. On the back side, it's one large hot plate. And on the near side, there's 4 condensation plates, so we can measure the temperature that these things. So the idea would be you'd have to pump in a lot of high current into this one Peltier device to try to cool this one size plate. If you had 4 Peltier devices, you could put less power, less current into each one and spread it out a little bit. So the idea was to try to figure out what configuration, 1, 2, 3, or 4, and potentially even more of them, would be the best arrangement of TECs. And we did that using the Solidworks simulation to try to figure out which was the optimum configuration, because we didn't want to build multiple units. We wanted to simulate it, figure out which one was best, and then move forward with that on the actual build. Here's some of the different configurations of the heat sink. So the hot side of the Peltier device would be bolted directly to this part of the heat sink. And the idea, you're trying to get the heat away from the hot side, and it's being through conduction through the back, through this aluminum heat sink. And there's air blowing around this in a contained cylinder here. So you're pulling the heat out through conduction and also through convection into the air. And we also tried different configurations using heat pipes. We'll talk about a little bit later. These are copper heat pipes. They work on a phase transition concept, and they're very efficient if you can get the hot side hot enough to boil off the water. And we'll talk more about how those operate when we get into the details of the simulation. But those are the heat sink configurations. Here is a early simulation. We purchased some, let me turn on this camera over here and let you take a look at this thing. So here is the some cooling assemblies that we purchased from Adafruit. So it's got a heat sink, a fan blowing. On the other side of this condensation plate are is the Peltier device. So the cold side is connected here. The hot side is touching the heat sink, and there's that insulating foam that's in there to keep that heat from just passing through the Peltier device and not over to the other components. So we did some early simulation, and you can see the temperature profile on this condensation plate varies quite a bit. It's going to get much colder in the middle and not as cold on the outside. And so we did some of that early simulation to just to quantify what Solidworks simulation was doing and how it compared to the results we were getting on the real hardware. Here's the another simulation we did. Here's the fan. We didn't have all the details of the fan with the blades and everything. We used a Solidworks simulation fan component. We'll talk about later. But you can see as you run the video here, if I can get it to go. Here we go. It gives you nice flow curves and visualization of how the flow is going. The velocity of the flow, you can see it slows down as it gets toward the end here. But this helped me design these ducts, these air ducts, to get the air flowing directly across those heat sinks. So that helped. We used this simulation to help optimize the configuration, the geometry of those air ducts as we went through the design. And here is it's a rather long video here, but we can look and see. This is a FLIR thermal camera, and you can see I've got one condensation plate here, and over time the temperature's going down. And if you speed this thing up, see how I can do that. The temperatures go down, and I apologize, I'm not sure why it's not running, but it takes a while to get to steady state. But over time, you can see how that temperature varies across a condensation plate. All right, so let's talk about the crux of the talk, which is how do we use these simplified black box entities in flow simulation to get the answers we want. So there's 3 devices that I used: heat pipes, axial fans, and these Peltier devices. So these heat pipes are extremely complex heat transfer mechanism. It's a phase transition. It goes from liquid to gas, and Solidworks simulation will not handle phase transitions. And so instead of using a complex simulation, we just use an equivalent thermal conductivity data from the manufacturer. And so I went to the manufacturer. We'll show a slide here in a minute. Talks about that from ATS, Advanced Thermal Solutions. The other second black box device we used was for axial fans. And so these axial fans, you've got these blades and the geometry, and if you want to do a simulation for an actual fan, you've got to turn on, you have some kind of rotating volume to simulate the blade spinning around. And that's so complex, we don't want to deal with that. The only person that would do something like that would be the manufacturer of the fan, maybe have to do something. But we've got, instead of that, we're going to use the flow curves from the manufacturer. They publish those data sheets with their products, and we can input those pressure flow curves right into SolidWorks simulation, and it will simulate the operational range of the fans themselves. The last item, the last entity I used was these thermoelectric coolers, and that's like the other 2. They're a very complex mechanism for heat transfer. It's at the atomic scale. There's a bunch of physics involved. So instead of dealing with that, we just use the performance data, the TEC performance data from the manufacturer. We can input that into SolidWorks as parameters, and we get those from Layered Thermal Systems, who manufactures these heat sinks. Manufactures the Peltier devices. So those are the 3 different black box entities that we used in SolidWorks simulation. So let's go through those one at a time. And here is showing a data sheet from ATS. It uses, this one I chose, it uses distilled water. So it's a hollow copper tube, and on the inside it's got this centered wick porous material that uses capillary action to pull the water out of the hot end. The left end would be the end that's getting hot. It's under a vacuum, so your boiling point of water under a vacuum is very, very low, which means it doesn't take that high of a temperature on the left side, the hot side, where you're trying to extract the heat. You heat that up, it heats up that water, and it boils well below 212 degrees, 100 degrees centigrade, because it's under a vacuum. And it wicks down to the right through that centered wick. As it gets to the other end, you start cooling it with the heat sinks that you saw on the test system we built. And when it gets to the right side, it condenses back out into liquid, and you get a nice large heat transfer doing that. And then it goes back across to the left, back to the hot side, and the process repeats itself. So instead of trying to simulate that with geometry and all the complicated physics involved, what you do is you tell SolidWorks just a few parameters. And so you tell it which face the heat's coming in and which face the heat's going out. You can see that pop-up window from SolidWorks simulation on the left. That's all you have there. So you tell it where the heat's going in, the face the heat's coming out, and then you give it an effective thermal resistance. You type that in. It's a degree C per watt. That's a typical measurement of thermal resistance. And you get that straight from the manufacturer. So if you operated at these temperatures under these conditions, then the equivalent thermal resistance will be this value. You type that into SolidWorks, and it just does that for you without having to do all the complicated phase transition calculations. All right, the next item is talking about these fans. So here's the fan I use, the Coleman Rotron fans. There's the part numbers, nominal voltage. Stall current would be the current at which it would pull if you locked up the fan blade. So that would be a worst case condition. You got a speed and you got rated airflow. And the rated airflow is if you've got the fan just sitting on a table where there's no, it's not pushing air through any device, it's just open on both ends, you're going to get that full rated airflow of, in this case, 235 cubic feet per minute. The problem with that is you can't use that because it depends on what your system. And so if you've got a bunch of blockages and a bunch of pressure drop between the inlet and the outlet, then that flow rate is going to go down, down, down. Eventually it would go to zero if it stalls out completely. Say you mount the fan to a closed enclosure with no outlets. You put the fan on the top, you bolt it down, you seal it, and run the fan. Well, there's going to be no airflow because it's got too high of a pressure drop. You can't push any air where there's no exit. So that's what these fan curves are for. So let's go to the next slide and look at this fan curve up closer. And we've got flow rate on the x-axis, cubic feet per minute at the bottom, and then metric units at the top. The vertical axis is the static pressure that you're pushing against. And our curve, ours was this B model, so it must be this green one at the bottom. So you can see the 235 cubic feet per minute happens only when the static pressure you're pushing against is zero. So that'd be the case with the fans just sitting out in the open. As you start building up static pressure higher and higher, the flow rate is going to go down, down, and it has these telltale curves that look like this, have a little flat spot in the middle. And if you went all the way down and you tried to push against 0.8 inches of water pressure, then the flow would go to zero. So when you're operating your fan, you're going to be on this curve somewhere, and you just tell Solidworks simulation, flow simulation, what that curve is, and then it works out and iterates to find out what that pressure drop is and adjust the flow rate accordingly. And here's the results here. They've got built-in fans in the Solidworks library. You can just pick different manufacturers and part numbers. If they don't happen to have your particular fan, you can just go create one, and it asks for things like the rotor speed, how fast it's spinning, the size of the hub and outer diameters of the fan, direction of rotation. And over here on the right, you can see this is that fan curve that I'm generating from that data sheet. And so what I do is I input points over here. This is the point. This is the volumetric flow rate, and these are the pressures at those points. So I just recreate the curve with those data points, plug that into Solidworks simulation for this particular fan, and then I give it some more properties down here. This is where you put in the rotor speed, hub diameters, and it just again iterates to find the flow rate based on your pressure drop through the system that you're pushing against. And so that's much more easily solved than trying to model the blades and have them spinning, pushing air around. So this is the second smart entity talking about. And the last one was the Peltier devices themselves. So the manufacturer, in this case, is Laird. They build these modules. They're like the image we saw before. They're made out of some ceramic material and have those end-peak couples that make the magic happen in the Peltier effect. The data sheet down here at the bottom right, we're going to talk about this in a minute. These are the performance specifications. And like we said earlier on those curves we looked at, there's different operating conditions, and most of these manufacturers rate them at a hot side temperature. Hot side temperature of the Peltier device is 25 C. These values apply. If the hot side of the Peltier device gets up to 50 degrees C, these apply. So if you put these parameters into the Solidworks Flow Simulation thermoelectric cooler entity, you give it the amount of the Q max, the amount of heat that's being pumped across the system, and there's different values depending on what the operating temperature, what the hot side temperature is. You put in two data points for the delta T across the Peltier device. There's two different values. Same thing for max current and the max voltage. And this module resistance doesn't come into play. But these other parameters all get put in similar to how we did the data points for the fan curves. and what that looks like when you put it into SolidWorks in this next page. And so I'm just using the information from the previous page. And so I've got to put in these parameters at both the hot side temperature of 25 degrees C when the hot side is 50 degrees C. So in this case, there's 2 data points. And so this particular property box down here, this is for these first data point here. It wants to know the maximum pumped heat. So I put in the temperature, 25 degrees C, it pumps 80.9 watts. If it gets up to 50 degrees C, it can pump 88.8 watts. Put those 2 data points in there, and it iterates through depending on the conditions that you're seeing in your simulation. You also put in maximum delta T. This is from the previous page from the manufacturer. This is the delta T between the hot side and the cold side when the hot side is 25 degrees, and this is the maximum delta T across the device when the hot side gets 50 degrees C. So you put those in, and then here's the results of that sample thermoelectric cooler assembly we bought. And as all good simulations, you're asking for the results. So here's the cold plate temperature. Oh no, excuse me, condensation plate temperature. So I got down to about 45 degrees or so on the condensation plate. And depending on where you are on the face, it's colder in the middle than it is at the edge. You can see the range of temperatures are pretty tightly grouped there. This is the temperature of the cold side of the thermoelectric cooler. Here's the heat transfer rate. We'll look at this in a minute. This is the cold side heat flux. So this is the heat going across the cold side of the thermoelectric cooler. So that's how much heat is being transferred out of that condensation plate to try to cool it down. So it shows here about 15 watts. And the last thing to look at is this. This is the operating amperage. And so, again, when these thermoelectric coolers are operated, depending on lots of parameters, including the hot side temperature, the amount of heat that you're trying to move, it adjusts and knows what that, or predicts, simulates what that current would need to be to operate in the ranges based on those values we put in to the thermoelectric cooler device in SolidWorks Flow Simulation. So these are the results. Here's some temperatures of the condensation plate, and these look like the hot side temperature for the heatsink, I guess. Yeah, heatsink temperature contours. So you can push these out in SolidWorks Flow Simulation. So you grab those numbers, and we'll go to the next slide. And this is how I figure out what power we're using. And so here's those delta T's we saw. So the hot side was 138. The cold side was 41, so that's a delta T of 97 degrees Fahrenheit, which is 53 degrees Celsius. So the delta T across the device was 53 degrees Celsius from the simulation data. We also saw that the operating current was 3.6 amps. So we go look at these performance curves, and the best one was the 50 degrees C curve. And so we use that one, and that's his first curve on the left at the bottom down here. And if I choose the delta T, was 53 degrees Fahrenheit, 53 degrees Celsius. So the bottom right curve, we're down here. We see that we're using 3.6 amps. So here's the different current depending on what delta T you have and how much heat you're moving. And so we had 3.6 amps. So I'll come up here, and that little red cross right there is where 53 degrees Celsius delta T across the thermoelectric cooler. And if you're operating at 3.6 amps, then we should be moving about, 12 watts. And so the simulation told me I was moving 15 watts. And the data on the manufacturer's chart said they were should really be pushing 12 watts. So that's pretty good correlation between what the manufacturer is saying and what the model says, which is always what you want to do when you do a simulation. So once I get those values, I go to this other chart, and I can figure out what the operating voltage is. So I know I'm still at 53 degrees delta T across the face of the thermoelectric cooler. I again go up here to 3.6 amps, picking the right set of this family of curves based on these numbers. And then I come across here, and I can read that the voltage is going to be operating at about 10 volts. So I can extract that from the simulation, and I can compare that to my power supply that I'm looking at when I'm running this thing. When it gets to steady state, it should be pushing 3.6 amps into the thermoelectric cooler at 10 volts. And I can compare that and make sure the model's matching. Finally, I can finally get to this coefficient performance number that I've been looking for. So on the right chart, I plug in 10 volts on this curve, and I find the delta T is somewhere between the blue curve and the red curve, 53. So I tried to find some place that was partially through there, so I got that point right there. And I come over and read the coefficient of performance, and I'm at 0.42. And if I've got multiple simulations I'm doing, I can do that same calculation, and I can figure out I want to get the best coefficient of performance for the particular configuration, and that's how I decided which one of those grid configurations I use, whether it's one thermoelectric cooler pulling a lot of current, trying to cool the whole plate, or if I've got 3 or 4 of them that are taking less current each, but are operating at lower temperatures. I find out which one's got the best coefficient performance, and I use that to decide which configuration to build from an actual test system. And the last equation here just gives me the power. I know it's operating 10 volts, 3.6 amps, so I'm using 36 watts of power to run this thing. Okay, so let's talk about some closing thoughts and what we found out. So what I did was we did simulations. We actually did 1, 2, 3, 4, and 5. We started seeing that the larger number of TECs was giving me better performance, and so we actually did a simulation. We actually built a configuration using 3, 4, and 5 thermoelectric cooler grids, and so those are the ones we chose. We added 5 because it looked like the performance was getting better going from 3 to 4, so we wanted to build one with 5. So to compare apples to apples on these different configurations, the total power for each set of TECs on a particular grid, whether it was 1 or 4, anything between, the total power I fixed so that we could say that the same amount of power is going to each condensation plate. So I just set the constant current on my power supply and applied it to each of the TECs. And then during operation, as it cooled down, the voltage is going to change because of all the parameters that those things operate in. And once steady state's achieved, then I measure the temperature of the condensation plate and calculate the power consumed using the same equation we used before. And all of them I tried to have a target condensation plate temperature of about 40 degrees, so it doesn't get too cold that it gets close to the freezing point. So again, we chose, I had 4 and 5. We actually built 3, 4, and 5 TEC grid patterns we chose to fabricate. We fabricated those on the actual test configuration. And as I was mentioning before, it's very important on these simulations to verify that your model is matching what you're seeing. So I used a company called Vernier that makes a lot of test equipment, and they have a LabQuest 3 system that lots of these probes plug into. So I used some Bluetooth surface temperature probes to measure the temperature of not only the hot and cold side of the Peltier device, but also the temperatures of the heat sinks, so I could again correlate that the model was matching the simulation results were matching the actual hardware. And we had an anemometer we used to measure the flow rate through that duct. So I was getting those flow rates, CFM for the fans, based on the simulation. I would check to make sure that the air blowing through that duct actually matched that using the anemometer. And also I had a Fluke infrared thermometer that we use, and that FLIR camera, that thermal camera you saw, to help me get a feel for what was happening as far as over time. I didn't do any transient Solidworks Flow Simulation studies because the computation time was cost prohibitive, so we just did steady state. And so I would use those thermometers, that infrared thermometer and that thermal camera, to be able to verify that the model matched the actual test data. So final results was my thesis defense was successful, so they gave me my master's degree that I earned. So that was good. All right, well, that's all I've got for the presentation. You can see my contact information down there. You can see my 2 new cute puppies, Uppy and Fermi. So there's my email addresses, not only my consulting company, Summers Technical Services, but also at Austin Community College and Texas State University. So feel free to reach out with any questions to me if you have them. There's a cell phone number. If you call me, I probably won't answer, but if you send me a text message and let me know what you're up to, I'll definitely get back to you. YouTube channel, log on to the YouTube channel. I'd appreciate supporting there. So if you like what you see, there's lots of different videos, multiple CAD programs, but mostly SolidWorks stuff. Subscribe to the channel and hit that notification bell so you can get notified when I post new videos. So that's all I've got for today. Thanks for your time and enjoy the rest of the conference this week.